Hi, a continuation of buckling. So we drew this graph earlier, looking at deformation pattern, and we come out with this trend where moment is equal to EI d squared y over dx squared. So I would like to avoid some confusion that you might have. So what if now, I hope I can rotate this, right? So now if let's say my structure is rotated this way, okay, or I can flip horizontal, right? So you can see from here, do apologize, the text is a bit off. You can see from here that now you can form an equation where coming from our elastic curve equation. So from elastic curve equation, right, so we're working from our elastic curve equation. We get d squared y over dx squared, and this is equal to m over ei. And the moment we found, right, the moment by point Q is minus py, right? So from here, we know P, right? The P over here is our axial load, capital P, big P. Okay, is our axial load. Okay, so if we were to rearrange this equation where we have d squared y over dx squared, right, and plus by py over e high, and this thing is equal to 0. So this is my equation 7. So the parent function, right, of equation 7, if I may, to remind you, we have an expression with d squared y over dx squared plus by a dy by dx plus by by, the whole thing is equal to 0. So over here, this equation over here is a homogeneous second order differential equation, right? So it's a homogeneous equation. So the solution, or not the solution, so what I'm going to do now is I'm going to let small p squared is equal to big P over EI, right? And this will be equal to my B. Okay, so my B over here, meaning my B over there. So you will have, so equation 7, right? So therefore, equation 7, right, will become d squared y over dx squared plus by small p squared y, and the whole thing will be equal to 0. So for this case, the general solution so we will have imaginary, so based on two imaginary roots, imaginary roots. We know that the function, right, so this is a general solution. So this will be equal to e c1x bracket c2 cos bx plus by or c2 sin bx okay, and then plus by c3 cos bx. Okay, so as we know, this expression over here is equal to 0, because if you look at the expression over here, this is because a, or the coefficient on dy by dx term is equal to what? 0. So the decay, so this is how decay will die off. Okay, so this will be equal to e to the power 0, or you don't have any decay, so you have c2 sine bx plus by c3 cos bx. Okay, so from here we can rewrite this. So e to the power 0 is equal to 0 equal to 1, so it is equal to c2 sine bx plus by c3 cos bx. Okay, so we have that expression over there then. Okay, so from here, I think I did make a mistake over here. Is I call p, right? Sorry, p is equal to square root, okay, p over ei, and I'm gonna let p is equal to my b. Okay, I do apologize, I make this mistake earlier. So likewise, you still have this p squared. Okay, I do apologize over here, I made a mistake there. So this expression is still valid, right? So it's p squared because p over ei is still valid. So from here, you have y. So the general solution will become right. So y as a function of x is equal to a sine px plus by b cos px, and all these are small p, and I'll call this our equation number 8. So this is still a general solution. So now we are going to impose boundary conditions such that equation 8, right, will be unique solution. So before I go on, we know that if we were to plot this out, okay, so I'm going to plot this out. So this is my y, right, this is my y, and this is our x, which is our variable. We know we're going to see a graph like this. Okay, so this can be your y as a function of x is equal to c2 sine bx plus by c3 or yeah, c3 cos bx. Okay, so we're going to impose a boundary. So boundary condition number 1, right? So if we go back here, when x is equal to 0, y is equal to 0, so we're going to substitute x equal to 0, and y equal to 0 into equation 8. So 0 is equal to a sine 0 multiplied by x plus by b cos 0 multiplied by x, not x, p multiplied by 0, again p multiplied by 0. So we know that b is equal to 0 because cos of b, this is equal to 1. Okay, so we know. Then next we're going to substitute boundary condition number 2, where x is equal to L and y is equal to 0, and we're going to substitute this into equation number 8. So what we have done down here, as you can see here, so this is our boundary condition number 1, and this is our boundary condition number 2, because it's built in, as you can see, at xl y equal to 0, it's built in, that's why y is equal to 0. So from here you know that y at distance L is equal to a sine small p L. Okay, so we're going to reflect, and this whole thing, right, we know that y equal to L, this is equal to 0, so we need to reflect on condition, okay, conditions where a sine small p L is equal to what? 0. Okay, right, so we have to find when this is true, right? We have to find when this is true. So now we know that it's true when p, right, it's true where p small p bracket L is equal to n times pi, because sine of any whole integer of pi will be equal to 0. So where n is equal to 1, can be 2, 3, 4, and so on and so forth. So therefore sine n multiplied by pi will be equal to what? Equal to 0. Okay, so we know that. So from here, right, so I'm going to call, so from here we know that, so I'm going to call this equation number 9. Okay, I'm going to call this equation number 9. I think that is equation number 9. Yep, so I'm going to call this equation number 9. So from equation number 9, we know that from equation number 9, we know that p, small p, is equal to n pi divided by L. Okay, so note we already have the expression, right? So I forgot which equation is from. We have this case Oh, we did not call our equation. Note that small p is equal to square root of p over ei. Okay, so if we're going to, so this is my equation number 10, right? So that's big P. So this big P over here correspond to our axial load. So from here, we're going to equate 9 and 10. So we have square root big P over EI is equal to N pi over L. So I'm going to rewrite this expression, right? So this will be equal to P over EI, right? So this will be equal to N squared pi squared over L squared. Okay, so therefore the critical load P critical is equal to N squared pi squared over L squared multiplied by EI. Okay, so if we go look at the critical load or the stress induced by critical load, so it's critical load divided by A. So did I declare? So A, oh sorry, I did not declare. So A over here, so this is your, also your, to apologize for this, should have done it earlier. So we will have your A, so over here, this is your small, is your A, which is corresponding to your area. Okay, so that's the area that we look at. So the area from here, we know that the critical stress is equal to N squared pi squared over L squared area multiplied by EI. Okay, so we're going to focus on mode 1. Okay, we're going to focus on mode 1, where mode 1 deformation, where N is equal to 1. Okay, so we know N equal to 1. So the stress critical is equal to pi squared EI over L squared multiplied by area. Okay, let me write my L squared multiplied by area. So this is our equation 11. Okay, so note that the second moment of area where I is equal to AR squared, right? So we're going to introduce second moment. So we're going to substitute I is equal to AR squared into equation 11, right? So stress critical, so therefore stress critical is equal to pi squared E, and we know I is equal to AR squared divided by L squared A. Okay, so we can get rid of these 2 points over here, or the A's. So we can write this as pi squared multiplied by E divided by L squared divided by L squared over R squared. Okay. So this is our equation number 12. And L over R is also known as the slenderness ratio, and R is the radius of gyration. Okay, so equation number 12, from here, equation 12 is only valid. Yeah, I want to highlight this, valid with centric axial loading condition. Okay, so i.e. the load is applied on the neutral axis. Okay, so this is important to note. Why is that the case? Because when we derive our expression, the load is acting on our neutral axis. So coming down, this orange that's coming down, that is our neutral axis. Okay, I'll come back again to do another series on buckling. So this is just to introduce you the theory of buckling, okay, and the mathematical base of how we have a pi squared and Young's modulus to be involved in to calculate the critical stress. Thank you.